Good evening, Castle Point. This is 200 at 75. The 200-inch telescope on Palomar Mountain has reached 75 years old. This is the story of its design and its construction. This image, taken by the Hale in 1951, many years before I was born, is one of the earliest astronomical images that I can remember. I've seen it in books in a school library, and I thought, this is amazing. What is that? What's it made of? Why did it end up looking like that? So this image, perhaps more than any other, got me started in astronomy. And what I'm talking about this evening was prompted by reading this book, Glass Giant of Palomar by David Woodbury, written in 1939. And in that book, he describes Hale's early life and how he came to build the 200-inch. And on reading that book, I was inspired and thought this would make a really good talk. Hence, what you've got this evening. So I'll be saying a little bit about George Ellery Hale, the person who managed to be a billionaire whisperer and convince people to give him money to build the largest telescopes in the world. The 40-inch, then the 60-inch, then the 100-inch, and finally the 200-inch. I haven't got too much time to cover the early years, but I'll give a little bit of context. I'll spend most of the time talking about the 200-inch telescope, how they decided where to build it, how they made the mirror, and how they made the telescope. And towards the end, I'll try and bring it up to date and talk about what the 200-inch is doing now. And I'll finish with some acknowledgements. So, George Ellery Hale, a great astronomer in his own right, but that perhaps has been eclipsed by the fact that he had the vision and the drive to build the largest telescopes in the world. Not once, not twice, not 3 times, but 4 times over did he oversee the construction of the world's largest telescopes. So that started with the 40-inch refractor in Yerkes, and then he moved on to Mount Wilson, where he oversaw the building of the 60-inch reflector, finished in 1908, and then the 100-inch hooker in 1918. Each of these telescopes could be a talk in their own right, but of course I am just using these to build up to the fact that once these 3 telescopes were in existence, Hale started thinking about the next one. So barely was the 100-inch hooker in operation than Hale started trying to find money to build a larger telescope. Notice that these 3 previous telescopes, taking the record of the world's largest telescopes, they've gone up in aperture by roughly half as much again, from 40 to 60 and from 60 to 100. So the next logical step would be, if you've got a 100-inch telescope, you think about building a 150-inch telescope. But Hale decided not to be too incremental. He figured, why not go the whole hog and try and double the aperture rather than simply increase by half as much again. That's going to be rather expensive, and so it took him quite a long time. As soon as the hooker was finished in 1918, he started to figure out, we need money to build a bigger one. We need more light. And it took many, many years and many, many whispering to billionaires to eventually come up with the money. In 1928, he approached the Rockefeller Foundation and he persuaded them somehow to pledge $6 million to build not only the 200-inch telescope, but the entire observatory, which didn't exist at that time. $6 million back in those days, that would be a fraction of $1 billion in today's money. And he managed to get it all from one source. It took him a few years of persuasion, but he managed it. Where are you going to put such a venture? These days, we recognise the best observing sites in the world are the Canary Islands and the Hawaiian Islands and the high mountains, the high desert of Chile. But Hale thought a little more parochial. His argument was, well, all of the really important astronomers in the world are based in America and specifically in Los Angeles. Well, you can argue about that, but that's what Hale considered, that all of the really exciting stuff was being dealt with on the west coast of America. So he wanted the telescope to be not far away. If all the expertise, the astronomers and the optical workshops and the mechanical workshops, if they're all in Los Angeles, why would you put the telescope on the other side of the world? So he wanted to think about something close to Los Angeles, home base if you like. Mount Wilson already existed and had a few telescopes such as the Hooker telescope, and you can see that that's just on the edge of Los Angeles, which of course was growing and producing more and more light pollution. Not only that, but San Fernando and then San Bernardino were growing, and you can see that Mount Wilson is getting surrounded. So Hale figured we have to move beyond Mount Wilson, but he would still like to keep it close to Los Angeles. So he sent out scouting parties to various mountains in this map region, including, as it happens, the island of Catalina. But generally speaking, he sent out scouting parties to various mountains in the region and found at least half a dozen mountains that had exceptional seeing conditions. So he knew that the final resting place of his new telescope was going to be one of those half dozen sites. He took advice from some geologists as to which might be the best if they were all very similar in terms of the seeing conditions. The geologists said, well, some of your sites are quite interesting, but I would advise not positioning them on the San Andreas Fault. That's not a good place to put a telescope. But there is one place you've got on your list which looks rather suitable, Palomar Mountain. Why is that suitable? Because essentially Palomar Mountain is a lump of granite, 30 miles long, 10 miles wide, 25 miles deep. It is a few trillion tons of solid granite. Even if California has an earthquake, that is not going anywhere. So the geology and the seeing conditions said that Palomar Mountain was the place to put this new telescope. It's far enough away from Los Angeles that that isn't too much of a problem. There is another city to the south, San Diego, which of course is also growing, but that was considered to be far enough away that that wasn't going to produce too much in the way of light pollution interference. It's about 60 miles from Palomar to San Diego. So the sighting was decided, Palomar. Now, Palomar Mountain looks rather beautiful, especially in the autumn here. I visited it, more than 40 years ago. When I was a student, I went to Palomar Mountain. I had a look at the Hale telescope, was blown away by the engineering of the telescope, as well as its importance and significance, and the site generally. But I was there in the spring, and when you're there on a nice warm day with your sleeves rolled up, it's difficult to remind yourself that actually in the winter it can get rather cold. It's at an altitude of about 1,700 meters or so, and so you need to pay people to shovel the snow off the top of the dome every once in a while. The peak itself, Palomar Mountain, is at about 6,000 feet. The observatory is just a little bit lower than that, but you can see that access to the top of the mountain is via a very windy road, the so-called South Grade. All the equipment, remember there's no infrastructure at all at this site, it's basically just open parkland, so everything had to go up that road. Every piece of the telescope, every piece of the observatory dome, every piece of the observatory infrastructure had to go up the South Grade. So that was a little bit of a problem, but it was considered worth it for the stability of the mountain and the seeing conditions. So Hale has obtained the money and he's decided the site of the Palomar Observatory. Next question is, what is the telescope actually going to look like? How are you going to mount such a large telescope? Well, as amateurs, we're used to the idea that telescopes can be mounted in a number of different ways. For instance, the German mount, which requires a counterweight, the fork mount, in which the telescope is mounted inside a fork, but there's still quite a bit of strain on the equatorial mount itself. One of the most stable ways of mounting a large telescope is the so-called yoke mount, or sometimes called the English mount, where the yoke is supported on the north and the south side, and so you get a very stable arrangement even if the telescope is quite massive. It's interesting to note that the three previous largest telescopes in the world actually used each of these designs. The Yerkes 40-inch used the German mount, the 60-inch reflector at Mount Wilson used the fork mount, and the 100-inch reflector at Mount Wilson used an English mount. When it comes to thinking about anything more massive than the 100-inch, remember we're not simply going up half as much again, we're going up to an aperture that's twice as large. So the mirror is 4 times the area. The telescope could be 8 times the mass. And so German and fork mountings were effectively ruled out, and it was decided to go for something similar to an English yoke mount. But when deciding what it should look like, Hale wanted to make sure that the 200-inch did not cut any corners and did not suffer from the same limitations as the 100-inch hooker. And there were 2 limitations that he particularly wanted to try and avoid. One of them is related to the mount itself. The English or yoke mount of the 100-inch hooker means that no observations could be made within 30 degrees of the north celestial pole. If you look at the size of the telescope and the way the mounting is set out here, you can see that the telescope can't point towards the North Pole, which is of course the line joining the north and the south bearing of the yoke. So 30 degrees of sky was forever removed from the field of view of the Hooker telescope. That was one limitation Hale wanted to deal with. The second limitation was the mirror itself. The mirror of the Hooker telescope was plate glass, which expands and contracts quite considerably with changing temperatures. And that meant that unless you were absolutely sure what the nighttime temperature was going to be, you would have to let the mirror come to equilibrium with the nighttime temperature, and as it cooled down or warmed up, it would expand or contract and would distort. And it might be that the observing session of the astronomer might be ruled out for many hours whilst they waited for the mirror to come to temperature. So both of those limitations Hale wanted to deal with. Let's think of them in those orders. The yoke mount. If you want to be able to point to the North Pole, but you want a very stable yoke mount, what do? The solution was the iconic horseshoe yoke mount. So still a yoke in the conventional sense with the south bearing, but the north bearing is now a huge horseshoe, such that if you did want to point the telescope towards the north celestial pole, you could do that simply by having the telescope tube nestle in the middle of the horseshoe. And the bearing surface of the horseshoe is this huge surface that goes all the way around the outside, and that is supported by oil pads sitting on this North Pole mount here. So the horseshoe mount was a solution to the problem of not being able to see the whole sky from any particular latitude and getting rid of the limitations of the hooker. What about the second problem? The Hooker telescope mirror was made of plate glass. If we have a look as a side view of the Hooker mirror, there's the top of the mirror coated in either silver or aluminium, and we're looking into the actual side of the mirror itself, a greeny sort of glass. But notice that the glass has an awful lot of structure. There are striations, and perhaps more important, there are huge numbers of air bubbles because of the way the mirror was poured as a molten piece of glass and then cooled to room temperature. And that's part of the problem. As the mirror expanded and cooled, then because of these air bubbles, different parts of the mirror would expand and contract at different rates and hence distort the surface of the mirror, making it unusable for sometimes many hours. Perhaps as much as half of the night might have been lost waiting for the mirror to come to equilibrium. If you have a mirror that's twice the diameter, that's 4 times the area, it could be 8 times as massive, and it could take even longer to come to equilibrium with the nighttime air temperature. And this was unacceptable to Hale. So in terms of scaling up the 100-inch mirror, you can't simply take the existing technology and just double all the dimensions. Using plate glass would result in the same distortions and would completely eliminate the idea of the Hale telescope being operational essentially all night. So Hale decided on a new idea: use low expansion glass, such that even if the temperature does change, the glass doesn't expand or contract anything like as much. Low expansion glass, well, we know it by its trade name, Pyrex. Pyrex is one particular type of low expansion glass that we're all used to. You can put it in an oven, take it out, and it won't expand or contract significantly as it cools down. Not only that, but they recognized that they needed to have a mirror which was not 8 times heavier. The length of time it takes a mirror to come to equilibrium depends essentially on the mass of the mirror and its surface area. So they had to come up with innovative ways of making a mirror to avoid it being substantially heavier. So how do you make a mirror? Well, you take a mould and you fill it with molten glass. As seen from the side, that's what it would look like. You fill it with molten glass, so you end up with a pancake slab of glass, essentially flat on its top and bottom surface. Once you've done that, you allow it to cool to room temperature. But you can't do that very quickly, otherwise, again, as the mirror contracts as it cools down, you would get unacceptable stresses induced in the glass. In the case of the Hooker telescope, it was calculated that if you scale that up and simply have a 200-inch that's the same design as the 100-inch Hooker, you wouldn't be able to cool it down from molten glass to room temperature in a few months. It could take years to cool down slowly enough to make sure you didn't induce any stresses. Perhaps as many as 5 to 10 years simply to cool down from the melt to room temperature. The Hooker telescope was smaller, so it didn't take quite as long, but once you've cooled to room temperature, you can take your slab of glass, you can grind the top surface down to the curve that you want, and then coat it with your metal of choice, perhaps aluminium, to give you a perfectly reflecting surface. So how are we going to reduce the mass? We can't use that same technique exactly as I've described. You have to come up with something a little more innovative. And the decision was to use a mould as I've described, but fill the mould with cores, those are fire bricks, and have the glass flow around those fire bricks. So again, you fill the mould with molten glass and you fill it up and then you cool it down. You're using less glass, and if you're using Pyrex or some similar low expansion glass, you can cool it down a little faster. Instead of taking 10 years to cool it down, you can cool it down in as little as 1 year without inducing any significant stress in the glass. Once it's cold, you can take those fire bricks out, the cores are then removed, and your top surface can then be ground to the right shape, just as you would for another mirror. And then again, you would coat it with aluminium. So the result is a mirror with exactly the same front surface. The figure and the polishing, etc. would all be the same, but now you have a big slab of glass which has got a ribbed back and lots of voids in the back, making it very light and very strong. Not 8 times the mass, but just a little more massive than the original Hooker telescope mirror. So that is what it looked like. Here's a drawing made by Russell Porter. I'll be saying more about his drawings later. Here's a drawing showing a section through the mirror, and you can see that some of the voids are actually used with these things that look like the top of pistons from an internal combustion engine. These are the mirror supports for the mirror. So the mirror cell has various support points that support the mirror to make sure that regardless of which direction the mirror is pointing in the sky, the figure of the mirror is absolutely preserved. Having a good support mechanism is absolutely vital. And some of these voids in the back of the mirror, and you can see again the ribs here, some of these supports are absolutely important in making sure that the mirror is exactly the right shape. So that's what the mould looked like, a large, effectively pancake shape, but full of these fire bricks. You can see that they occupy quite a large fraction of the overall volume of the mould, making sure that you use less glass. There's a large plug in the middle because ultimately this is going to act as a Cassegrain telescope, and so we need a hole in the main primary mirror, and that plug will provide us with the hole. So I realise that you can't read the text here, don't worry about that. This just gives you an idea of the layout of the Corning Glass Works. This is the firm that poured the 200-inch mirror. So there's a large tank over here in which the glass is melted, so there's a whole tank of molten glass. And then teams of workers use this very large ladle that looks like a very large ice cream scoop. They scoop up molten glass from the tank and then carry it over to the mould. And the mould here has got these fire bricks, and then teams come in with their ladles and pour the molten glass into the mould, and the glass flows around the fire bricks to give us the final shape of the mirror. It takes many of these ladles. Hundreds of times the workers had to scoop glass from the tank and then carry it over to the mould. And we can see that in action in these black and white videos from the Corning Glass Works. So a ladle is going into the tank, everybody jumps on the other end, and then out comes the ladle full of molten glass. Water is sprayed on the ladle to stop it from melting. From a slightly different angle, we can see that the ladle is put in upside down, and then it's dipped into the tank, and then rotated, and then everybody jumps on the other end of the lever, and out comes a ladle full of 100 kilograms of molten glass. The excess glass is scraped away. Water again is sprayed onto the ladle to stop it melting, and then the ladle is taken over to the mould itself and inserted and then turned through 180 degrees to pour the glass into the mould. Once that is done, the ladle is removed and any excess glass is poured into a wheelbarrow, which is then taken back to the original tank and recycled. So there's a still effectively of the same thing, a group of people carefully controlling the position of this ladle. You can see the weight is actually taken by an overhead rail system, and the person at the front here is in charge of deciding exactly where this ladle goes in terms of where into the mould the glass gets poured. So there's the mould kiln itself, or oven. You can see it's a brick oven, and the team here with the guy at the front deciding where exactly the ladle gets positioned to pour the glass into the mould. I'm guessing that this fellow on the left is a supervisor because he's wearing a hat. Now, there was a problem. In 1934, when the first glass mirror was made, they had a few problems. You can't see what's going on in here, but some of the fire bricks, some of the cores that are in here, unfortunately, some of them popped loose. And the fire bricks are lighter than glass, so the first thing they do is pop to the surface. Also, some of the bricks, you can see the entire oven is made of separate bricks. Some of the bricks on the inside walls fell off and again fell into the mirror itself. So these were removed once the mirror was cold enough to actually get in there and start to actually remove the bricks or the errant cores, but it caused huge gouges to appear in the mirror. These gouges were many centimetres deep. Now, it was thought maybe this is not irretrievable, because remember, we're going to have to grind this mirror to a particular shape, a parabolic shape. We are going to remove many tons of glass from the front of this mirror. Maybe these gouges don't matter. Unfortunately, when they did a quick check, they realized the gouges were simply too close to the edge. If the gouges were close to the center of the mirror, they might have been able to produce the figure of the mirror and get down to pristine glass. But because these gouges are too close to the edge, they couldn't do that. They decided this mirror could simply not be used, and so this mirror went into the Corning Museum, and they had a second crack at making the mirror in 1935. This was altogether more successful. They made sure that the oven, the kiln, didn't have any loose bricks, and they made sure that all the cores were firmly bolted down to make sure none of them popped to the surface during the process of pouring the glass or during the 1 year long cool down. And here's the result. You can see the back of the mirror being checked by an engineer here. It shows very nicely the ribbed structure that results from all of the fire bricks, all of the cores, and it shows you that some of them are circular. These are the positions where ultimately the mirror support system is going to be making sure the mirror is fully supported over its entire 5 meters diameter, over its entire 200-inch diameter, to make sure that it's properly supported. So the second mirror was inspected and declared to be stress-free. Here's a publicity shot from the Corning Glassworks, reminding us that the plug in the center, the Cassegrain aperture in the center of the mirror, is itself quite large, 1 meter or so in diameter. Again, another very nice view of the ribbed structure of the back of the mirror. Corning were very keen to use this casting as advertising for themselves. The eye that sees 6, I don't know how many zeros that is, that's an awful lot of zeros. What do they mean by that distance? Well, it was assumed that once built, the Hale telescope would be able to see about 1 billion light years. And 1 billion light years, if you convert it into miles, is that many miles. So the successful casting of the 200-inch, they did have a few problems. They had a flood of a river which threatened to hit the transformers that were keeping the ovens warm. That was a bit of a problem. They also had a small earthquake, but they overcame all these problems and produced a fantastic 200-inch mirror, which they then shipped off from the East Coast to the West Coast. So they sent the mirror over to Caltech in 1936. Here's the mirror, supported by apparently 1 strap. So this was something like 40 tons by the time they had got this to Caltech. And then the Caltech team had the job of figuring it, grinding it to the right shape. So this is the team that started that. A team of 21 men. Ultimately, it took them 11 years to grind the mirror. It shouldn't have taken quite that long, but as I'll explain shortly, something got in the way of their initial plans. So the team of optical technicians supervised the grinding machine. Here we can see the 200-inch mirror sitting on the grinding machine, a large rotating turntable. On top is the tool here doing the grinding, and that's on a gantry, so the tool can move backwards and forwards and the gantry moves backwards and forwards. So they would grind the mirror, and then every once in a while they would test whether or not they are grinding it to the right shape. And this is where the mirror support system is absolutely crucial, because the grinding is done whilst the mirror is horizontal. But to do the test, they pivoted the mirror so that the mirror was vertical, so that they could use the length of the optical workshop to do the optical test. So they had to be absolutely sure that when they're grinding, when the mirror was horizontal, they had to be absolutely sure that the figure did not change when they tilted the mirror to make it vertical. So again, the mirror support system that did that is absolutely crucial. Again, I haven't got time to talk about the details, but if any of you are engineering buffs, you might appreciate the technical challenge of making sure that many tens of tons of mirror does not flex in any perceptible way, despite the fact that the gravitational load can be extremely different between a vertical mirror and a horizontal mirror. I find it curious to realise that people back then still apparently had pipes in their mouths. I can't believe that people were actually allowed to smoke in the clean environment of a telescope grinding and polishing workshop. Maybe they just have pipes just because that's an affectation. So to make sure the mirror is the right shape as it was being figured, a knife edge test was done to make sure that the figure was what they expected. So in a knife edge test, you can see the gentleman here is doing that, and the knife edge was on the opposite side of the optical workshop to the mirror itself, and that gave them a pretty good idea to within a reasonable fraction of the wavelength of light whether they were making the mirror to the right shape or not. Whilst the grinding of the mirror was taking place, work began on the observatory itself. So in 1936 they started the foundations. They don't need a huge amount of foundations. Remember, Palomar Mountain is actually a huge slab of granite. So all they needed to do was drill some piles such that the building was anchored rigidly to the granite bedrock. So it took a little while for the observatory building to start to take shape. The walls of the building aren't very high, and before long they were at the height required for the track of the dome itself. And here's the track of the dome being ground to the right shape. Hale wanted the dome to rotate without appreciably affecting the telescope itself. So when the engineers asked, well, how smooth do you want the rails to be for the dome? Hale said, well, the nearest thousandth of an inch should be good enough. The bottom line is, if the dome weighs 1,000 tons, when the dome moves, the telescope should not be aware of the fact the dome is moving. There should be no vibration carried to the telescope itself. So quite a demanding feat in its own right. Once the track was laid, the rest of the dome could start the construction. And by 1937, the observatory dome was starting to look like an observatory. To give you an idea of what's going on inside, I'm going to use again drawings made by Russell Porter. So Russell Porter made a lot of rather incredible engineering drawings. He was a technical artist, and I'm going to use his pencil drawings, his graphite drawings, to illustrate some of the points I want to make here. So to start with, let's just look at a crop of one of his drawings that shows the telescope itself. Let's just make sure we understand how the optics work. Let's just make that a little bit fainter so we can see what's going on. So at the bottom of the telescope tube is the mirror. I haven't attempted to show the correct figure of the mirror. There's just a slab of glass. The telescope can be used at prime focus, which means light from a distant star hits the mirror and comes to a focus within the so-called prime focus cage. This is a cage. You can see the size from this gentleman astronomer sitting at the top here. This was basically the first telescope that was large enough such that at the prime focus there's a large enough space so that an astronomer could ride inside the telescope. For any telescopes that came along after the 200-inch, well, photography and CCD cameras obviated the need for the astronomer to actually be inside the telescope. So you could argue this is the first and last time that a prime focus cage was actually used effectively. So the astronomer could sit here and observe or use photographic plates to photograph wide-angle images of the sky using a focal length which is just, as you can see here, approximately 3 times the size of the mirror itself, an f3 prime focus. But below the astronomer, in the bottom half of the prime focus cage, there are a number of mirrors that can fold down to intercept the light path. For instance, if the astronomer isn't interested in prime focus but wants a longer focal length, then a Cassegrain mirror can be folded into position such that the light hits the primary and then the secondary and then goes through a hole in the primary mirror, which I haven't shown, to arrive at the Cassegrain focus. So you can see that the prime focus cage itself doesn't really block any light hitting the mirror, the main mirror, because the main mirror has a aperture, has a hole anyway in its center. So the prime focus doesn't really block any light. People might want to use the Cassegrain focus because of that larger focal length. That's what you would use if you wanted a higher magnification. So also, it's very useful because you can put a lot of equipment on the back of the telescope itself. The prime focus cage, as it's called here, behind the primary mirror, can take a large load of equipment without significantly altering the balance of the telescope. I've read that the total amount of equipment that can be placed in this position is about 1 ton, and that will not significantly affect the balance of the telescope. Instead of a Cassegrain mirror, a Coude mirror can be placed at the secondary focus, and then another mirror placed at the intersection of the declination axis and the polar axis, and that will send the light off the primary, off the secondary, off the tertiary, and then down the polar axis of the telescope itself into the so-called Coude room. The Coude focus is called the Coude focus because Coude is French for elbow, and you can see that we have this dog leg or elbow in the middle there. The idea of this mirror at the intersection of the right ascension and the right ascension and declination axes is such that this focus point does not change regardless of where the telescope is pointing. Regardless of the declination, regardless of the right ascension or hour angle, the focus of the Coude focus is always this point. And that means you can have extremely heavy equipment placed here because it won't move at all. It can either be very heavy or very large, and because it doesn't move, it doesn't affect the balance of the telescope. So that's where spectroscopy is usually carried out. Let's have a look at the construction of the telescope itself. It was made by a company called Westinghouse, and you can get an idea of the size of the main mirror by looking at this, which is the ring that holds the mirror cell, and I'm guessing that these are the various people at Westinghouse who are involved with the construction of the telescope tube. Some small pieces here give you an idea. There's part of the horseshoe. There's of course the telescope truss itself, and you can see it in various stages. I believe this in the bottom right is probably one of the declination bearings, one of the declination trunnions. In 1937, the tube truss itself was essentially ready, and there was not quite a topping out ceremony, but there's a celebration of the completion of the tube construction. A few dignitaries were invited. Perhaps you can almost recognize a certain Professor Einstein there. Einstein was a theorist, but he was very interested to know whether or not this new telescope would be able to see galaxies which might be able to prove some of his theories correct. Once the construction was complete, the parts were shipped over to the West Coast. But in addition to the tube itself, the mounting, of course, was a substantial piece of engineering. This is a small piece of the horseshoe mount. You can see the curve, the outer curve of the horseshoe. That's what is going to ultimately be the bearing surface, and there's the inner part of the horseshoe. So this is one of the two horns. You can see a lot of internal structure which is part of the bracing to make sure that the horns don't flex. But notice just how thick the pieces of metal are. The inside and the outside surfaces of the horseshoe are pieces of steel 4.5 inches thick, and they were bent into shape with a 12,000 ton forge press. Yeah, that's not a misprint. 12,000 tons were used to press these steel plates into the right shape. So this is probably just a publicity shot of two men measuring up. If it's not right at this point, you can't really change it. So again, it shows quite nicely just how thick these outside steel plates were. This gives you an idea of scale. The horseshoe was made in 3 parts because it was just infeasible to make it in one piece. So the horseshoe were made in 3 pieces and then bolted together. And then finally it was placed on probably the world's largest milling machine to actually make this outside surface as smooth as possible. There were lugs here to move it from A to B, but those were removed to produce a bearing surface which was perfectly smooth. Once that bearing surface had been manufactured, then the 3 parts of the horseshoe were unbolted and sent over to the west coast. The south bearing, it looks a little bit like a sort of telephone handset when you look at it like this. The centre hole is the actual south bearing itself, and these 2 large circular features at either end of this telephone, as it were, are the pieces that take the large circular yoke arms. You can see just how large these yoke arms are from the fact that a person can stand up inside them. I'm not sure why I found that surprising, but of course after a little bit of thought I realised of course they have to be that big, because at least one of these arms has to take the large declination motor that drives the telescope in declination. That hadn't even occurred to me until I thought about the construction through images like this. So all of these pieces, once they arrive in California, have to be taken up to the observatory 1 piece at a time. Remember that rather wiggly drive that every piece of equipment has to go up in order to get from sea level effectively up to the top of the mountain. So you can see, perhaps you can see the name of the company that was employed to do this, Hazard and Sons. And here they take what appears to be part of the horseshoe mount and maybe a few other bits and pieces. There's a truck at the back pushing, and there's a truck here and another truck at the front. So it took 3 trucks to get some of these heavy pieces up the winding road. To the best of my knowledge, they didn't have any serious accidents. All the pieces made it intact. When they arrived at the observatory, everything went inside the observatory by going through the observatory floor. A big square hatch was opened up and in came each of these pieces. This particular view actually shows very nicely not just the arrival of the south yoke, it also shows you the inside of the dome and the fact that the dome is riding on these many bogies, each of which has got 2 or 4 wheels, and you can see how the weight of the 1,000-ton dome was distributed over a very large number of wheels all around the edge of the observatory. So here's part of the horseshoe arriving. You can see there's the yoke already arrived. There's part of the telescope truss itself. Everything came through the floor of the observatory. I don't quite understand why they didn't crane it in through the slit of the dome itself. Maybe the slit just wasn't quite big enough for some of these pieces. Once everything was inside the observatory, it's only a question of putting it all back together again. Essentially, everything had been built by the manufacturers and then disassembled. Once it was in California, everything is constructed again. So this is now 1939. Everything is being put together. You can see one of the engineers here. No such thing as health and safety. No harness, no hard hat. No need for those back in the 1930s. Here's somebody working on the prime focus cage. Okay, this guy does have a hat. It's not a hard hat, but at least he has a hat. He's just making sure that everything is in place. Again, it gives you an idea of the scale of the truss of the main telescope as well as the scale of the prime focus cage. When everything was bolted together, they had to make sure it moved the right way. And here's a short video showing the telescope pointing as far south as possible. I'm sure they never actually pointed it to the south horizon because A, there's San Diego there, and B, there's an awful lot of murk regardless. But they wanted to make sure the telescope moved the way they thought it should move. So here's an engineer. I guess he's an engineer because his sleeves are rolled up, and they're just making sure that everything works the way they expect. When it comes to the movement of the telescope, everybody can appreciate, I'm sure, that the mirror needs to be made to very high precision. But if you want to move a telescope and point it to very high precision, then the gears need just as much thought as to how you're going to make them. Hale wanted the telescope to be such that it could be pointed with arc-second accuracy. Now, maybe you take that for granted with modern electronics and modern gearing. But remember, this is 500 tons of steel. By the time you've taken the telescope tube and the mirror and the horseshoe mount into account, it is a 500-ton beast. And yet they still wanted to be able to point to arc-second accuracy. That meant the gears, especially the right ascension and declination main gears, had to be made to phenomenal accuracy. And it took almost as many years to cut the right ascension and declination gears as it did to actually grind the mirror to the right shape. So they built themselves a grinding machine and they ground and polished the teeth of the right ascension and declination gears to the precision required. So that, I believe, is part of the early grinding process, and the polishing process then continued until they had the teeth exactly the right shape and as smooth as possible. How did they check everything was right? Well, they got an expert with a pipe to run his fingers over each of the teeth to make sure that everything was perfect. And then they did a final check by running a worm against the worm wheel to make sure that everything moved exactly as it should. So how big a motor do you need to move a 500-ton telescope? Well, the motor is given here, and you can't perhaps judge the size of this motor until you introduce a little something that you do recognize. There you go. The motor that either tracks or indeed slews is actually tiny. The tracking motor is only 1/12 of a horsepower, and even the motor that slews, that has to accelerate the 500 tons and then decelerate at the other end, even that is only a few horsepower. It is quite incredible how little is required because the mechanism and the flotation of the horseshoe on oil pads is so good, there is so little friction, you need very little force to simply move that mass. Let's have a look at some of the drawings made by Russell Porter, this technical artist who made drawings between 1937 and 1940. I'm going to show some of these drawings because they give us a wonderful insight into the design and construction of the 200-inch telescope. It might be that some of these drawings really don't come across on a Zoom screen, so I'm going to make the originals available to you as PDFs by sending a link after the talk so you can look at them in more detail. But the drawings are really incredible. They are very accurate, they are very detailed, and most of them are cutaways. And they are cutaways in the imagination of Russell Porter, because he didn't have the telescope in front of him. He had blueprints and drawings, and from those he tried to figure out what will this look like in 3D and what will it look like if we draw it in cutaway. And he produced these drawings over a few years, and the amount of detail is absolutely stunning. In this particular case, there's a 2 horsepower slewing motor down at the bottom and a 1/12 horsepower tracking motor down at the bottom there. There's also a large mechanism that would allow, it's effectively a analog computer, it's a mechanism that would allow compensation for refraction through the Earth's atmosphere to take into account the fact that a star isn't quite where you expect it to be, and if you want arc-second accuracy, well, you take into account refraction through the atmosphere. The fact that they thought about things like that and designed an analog computer to do that, I find quite incredible. I'll go quickly through these drawings because, again, some of the detail might not come across on the screen you're looking at. This gives you a close-up of how the huge horseshoe mount is supported by an oil pad system to reduce the friction way below what you would expect from ball bearings or roller bearings. Some of the detail in the south yoke, and you can see that that's how people would actually access the inside of the hollow arms of the yoke. Here's one of the two yoke arms, and one of those arms contains the declination motor, which then drives the large declination wheel to move the telescope in declination. That's simply a view looking into the prime focus cage, and that's an indication of what an astronomer might be doing, sitting at the so-called pedestal in the top of the prime focus cage, perhaps with a photographic plate. Perhaps the astronomer is checking that the photographic plate is imaging what he intends it to image, and it might be that the astronomer needs to make small adjustments to the telescope, which he can do remotely from within the prime focus cage to get everything lined up perfectly. In the bottom half of the prime focus cage, so the picture we just saw was up here at the top, in the bottom half of the prime focus cage, this is where mirrors would fold down to give us either a Cassegrain mirror or a Coude mirror with a different focal length to give us different optical configurations. And if we send the light down the Coude axis through the polar axis of the telescope, it would end up in the Coude room, where it would bounce off some mirrors, probably bounce off a diffraction grating to produce a spectrum which would then be recorded at the bottom of the Coude spectrograph. We'll have a look at that in just a moment. So, is it finished? Everybody thinks that the telescope is done. It looks like the tube construction is complete. The telescope mount is complete. The mirror looks like it's within a few millionths of an inch of the correct figure. So it looks like we're just a few months away from finishing. But it's 1941 and America is about to be dragged into the Second World War. That means everything gets shut down, or at least repurposed. The mechanical workshops, the optical workshops, are requisitioned by the military for other purposes. And so nothing happens on the Palomar Observatory project until the war is over. So come 1945, they return to the mirror. We notice two things. One, the mirror is now starting to take on a dish shape because the parabolic shape of the mirror has now been established. It's approximately 10 centimeters deeper in the center compared to the edge. That's the amount of curve on a mirror of 5 meters diameter. We also notice that the 21 men of the original team have now been complemented by the fact that we have a few women on the team. Excellent. Come 1947, they've made the mirror as close as possible to what they think is the correct figure. They can do a knife edge test to make sure it is what they think it is, but the real test of a mirror is to point it at a star. So when they think they've got it as good as they can get it, the mirror is taken up the mountain. Yes, up that 12-mile windy road. Once they get it there, they can start thinking about actually putting it in the telescope. In 1948, they had the dedication ceremony. So at this point, the 200-inch telescope became the Hale telescope. That's why I say that the Hale telescope is 75 years old, because it was dedicated and named the Hale telescope 75 years ago. Unfortunately, George Ellery Hale had died a few years earlier and never got to see his dream completed. But I like this particular photograph simply because you can see how many people there are on the observatory floor. I believe there were something like 1,000 people there that day. It reminds you just what a huge observatory it is to take such a large telescope. So the mirror has arrived on site, and in 1949 they basically put the mirror without a coating yet. It hasn't got its glass coating. We can still see through the top glass surface to the voids underneath. The mirror would be placed in the telescope, pointed at a star, and even without a metal coating they can still get an image from a relatively bright star, and they can see whether the star is perfectly focused or not. If it looks like any part of the mirror surface is just a little bit too high, then they put a mark. These aren't dust specks or detritus, these are marks put onto the mirror telling the polisher that these points are just a little bit too high, perhaps a few millionths of an inch too high. So the mirror would then come out and the polisher would then start polishing those regions to try and bring them down. When it came to the last little bit, the polishing was not done, certainly not done with a machine. It was done by an expert polisher, perhaps just putting a little bit of jeweler's rouge on his thumb and stroking the surface of the mirror to take the last millionth or two of an inch off the surface. The mirror would be put back in the telescope, pointed at a star, and again checked, is there any part of the surface of the mirror that is ever so slightly too high, making the mirror imperfect. This was carried out back and forth a few times until the mirror was declared as good as it could possibly be. And at that point, the mirror surface would then be coated in aluminium and the mirror placed in the telescope. So here's a view on the left, a publicity photo showing an astronomer sitting in the prime focus cage. Again, there's the drawing on the right reminding us that that's what we're talking about. Hubble, as in Edwin Hubble, not the telescope, the man. Edwin Hubble was interested in using the Hale telescope because he had used the 100-inch Hooker telescope to take spectra of remote galaxies. It seemed to indicate that the universe was expanding with a constant that we now know as the Hubble or the Hubble-Lemaitre constant. So Hubble was very interested in using the Hale telescope in order to look at more distant galaxies. Remember, the prime focus telescope is actually open to the elements. There's no enclosure as such. And I'm sure that all the astronomers that did go into the prime focus cage, especially those that were taking data during the winter, were very keen to use the war surplus electrically heated flying suits that kept them toasty warm whilst they were in that rather cold environment. We can get an idea of what it's like by this short video. Here's an astronomer starting a session. He's going to put a photographic plate holder into the top of the pedestal. He's sitting in the prime focus cage itself. In goes the photographic plate holder. Then he puts a photographic plate into that. No, that's not the plate. Put it back. In the dark, he will open up a box and then take the actual plate itself. The photographic plate will then be placed in the holder. That's it. And then the back of the camera gets placed. Okay, he's got the idea now. That's fine. So the back of the plate holder goes into position to hold the plate firmly in position. Then the astronomer can use the small telescope on the left to actually check whether or not the telescope is pointing in the direction he wants. He'll move the little telescope until he's pointing at a guide star, which he'll use to make sure the telescope is tracking correctly. Once he's happy that he's got the guide star located, he will then probably, I don't know, check he's got his sandwiches ready for the night. Yeah, okay, sandwiches ready, thermos ready. Okay, you can start the exposure, expose the photographic plate, and off you go. And every once in a while, he would check the guide star and make sure the telescope is pointing in the right direction. If there was any sign of deviation, he would have a little controller there at hand to allow him to make small adjustments to the right ascension and declination motors. Rather than being in the prime focus cage, if an astronomer wanted to work at the Coude focus, remember the light comes down the polar axis into the Coude room, according to this drawing I showed before. This video I'm about to show is taken from the opposite side, so it looks mirror flipped. So here we have the astronomer checking that the light is coming down the polar axis and the object of interest is lined up. He would then get rid of that small telescope so that the light is now falling on the entrance slits of the spectrometer itself. He will check that the light is on the slit, then move into the Coude room itself, where the light will bounce off mirrors and a diffraction grating and produce a spectrum down at the bottom. So the astronomer would place a photographic strip at the spectrum and then leave the room, and then the observation of the night can begin. There's another person in this picture, as well as the astronomer in the prime focus cage, as well as an astronomer standing down here in the Coude room. There's one other astronomer in this image. Perhaps you can see him or her. They're down there in the bottom right. This is the night assistant. This is the person that works in tandem with the astronomer, and they're always in contact with the astronomer. At the control desk, the night assistant controls where the telescope is pointing. It's a very clever system of so-called self-syn or self-synchronized motors, whereby part of the indication here is where the telescope is actually pointing, and part of the indication here is where the astronomer wants it to point. And using self-syn motors, basically the telescope moves until those two readouts are exactly synchronized, and then you know the telescope is pointing where you want it to point. A very clever idea. And again, I've got no time to go into the details, but if you've got any interest in electronic engineering, that's quite a wonderful story in its own right. So a few years after it started, it's dedicated in 48, its mirror was finished in 49, and so first light was effectively in 1949. And this picture of the horse head that I started with was taken very soon after the operation of the telescope had started. It's a wonderful and emotive image, but I thought it was rather interesting to compare it with another of my favourite objects, the Helix Nebula, taken at about the same time, 1952, because this telescope has got a parabolic mirror. And for those who know their optics, a parabola will focus perfectly on the optical axis. In other words, a star at the centre of the field of view should be perfectly focused. But a parabola will distort the further away you get from the centre. In fact, you can actually see this. This was taken at prime focus because this is a very large object. And if you look towards the edge of the image, you find the stars are looking very non-stellar. The stars are suffering from chromatic aberration, or coma. This is something I discuss in a separate talk, talking about how the laws of physics and the laws of optics dictate telescope design. But that is not a problem. Hale decided to go for a parabolic mirror because that was a tried and trusted technology. Most large telescopes these days don't use parabolic mirrors, they use hyperbolic mirrors, a different conic section, and that gets rid of this particular aberration. But at the time, Hale knew about hyperbolic mirrors, but didn't want to risk the project by trying to make one. He stuck with the tried and trusted parabola. So yes, a parabola will distort if you're using very wide angle. Not a problem if you're at the Cassegrain focus, not a problem if you're at the Coude focus, only if you're taking very wide angles. And if you want a wide angle picture that looks prettier, you can put a so-called coma corrector in if you really want to. But that wasn't the reason the Hale telescope was built. It wasn't built to take pretty pictures. It was built to study distant objects carefully, accurately, and to obtain their spectra. You could say, what's it doing now? It was a wonderful telescope in its time, but has it been doing anything recently? Well, for instance, not that many years ago, it was used as a testbed for adaptive optics. The 5-meter mirror itself cannot change. It's a large monolithic piece of glass. But if you want to test out a piece of equipment, then the Hale telescope is actually a great way of doing it. If you think you've got a piece of equipment, for instance, to allow you to use adaptive optics, because the Cassegrain focus, remember, you can put an enormous amount of equipment there, maybe up to a ton of equipment can go at the Cassegrain focus. If you've got a prototype, even if that prototype is rather big and heavy, you can put it on the Hale telescope and see how well it works. And here we've got a comparison of the moon Ganymede taken with the Hubble Space Telescope and taken with the Hale telescope using adaptive optics. And you can see just how good you can get a 5-meter mirror. Bear in mind, the ordering of these two is probably not what you think. The left-hand one is the Hale 200-inch telescope with adaptive optics, and the right-hand image is from the Hubble Space Telescope. So if you get it right, you can use modern technology, even on an old telescope, and prove certain aspects of new technology and new instrumentation and new equipment, and then perhaps you can go away and use it on some other telescope. So the Hale telescope is still a workhorse because it is so well made. It can use equipment, even heavy equipment, and it can prove concepts where you wouldn't want to necessarily tie up a 10-meter telescope or anything larger, where you can use the 5-meter telescope effectively to do a lot of proving ground work. It's actually been used also for doing exoplanet work. One of the images of exoplanets, even before the Hubble Space Telescope was imaging exoplanets, the Hale telescope had done the same with adaptive optics. And also the Hale telescope is going to be used for the future Psyche project, for instance, where the data from the Psyche space probe is not going to be sent back via radio waves, it's going to be sent back by laser. And the Hale telescope is going to be used to pick up that laser. So the Hale telescope is still doing good work. To keep it operational, you don't just need to give it a new lick of paint every once in a while, you need to keep the mirror clean. So every 18 months or so, they take the mirror out to give it a clean. If anybody is of a nervous disposition, perhaps you want to look away now, because to clean a mirror like this, you have to really clean it. So yes, they give it a damn good wash to get the rubbish off, and then they use acid to remove the metal layer. Now they're down to glass, and now they give it another damn good clean. Trying not, of course, to change the figure of the mirror, but to get it as clean as possible so they are back to the pristine glass, back to the pristine figure. Once they've got it in this state, they can take it back into the evaporator and evaporate another coat of aluminium and then put it back in the telescope. Hopefully it's good for another year or two or more, even under the Californian skies. So that is the Hale telescope today. A really beautiful thing and something that's been operational for 75 years. It's well worth a visit. As far as I know, it's still open to the public. You can't necessarily observe through it, but you can visit Palomar Mountain, you can visit the dome, you can see the telescope in action. So I've been telling you about George Ellery Hale. I've had a little bit about his background, but not as much as I would like. I've spent most of the talk telling you about the 200-inch telescope, how they selected a site, how they made the mirror, and how they made the telescope. I've tried to bring you a little bit up to date in what it's doing now. So let me acknowledge the fact that I've obtained a lot of information from the Caltech archives, and also Scott Cardell, a public affairs coordinator at Palomar, produced a blog for many years. Unfortunately, it's no longer running, but for many years he produced a blog saying what the telescope was doing now and covering a certain number of aspects about the history of how the Mount Wilson and Mount Palomar came to be. The Corning Museum of Glass has a number of useful videos, some of which I've shown, of the mirror being made. I'd like to acknowledge the fact that I got inspiration in the first place from this book, Glass Giant of Palomar by David Woodbury. It gives a lot of information about Hale's early life and how it led to the building of the 200-inch. You can see it was written in 1939, so it was actually written before the telescope became operational. Top right and bottom left, the Giants of Palomar drawings of Russell Porter are shown in these two publications, and I'll send you a link to a PDF which shows some of these beautiful drawings in more detail. The book in the bottom right, Perfect Machine by Ronald Florence. A more contemporary book, it's not being arrogant when it's called The Perfect Machine. It's simply reflecting the mindset of the people who build it. They tried not to cut any corners. They tried not to make any compromises. They wanted the final telescope to be as close to perfect as they could possibly make it. So the Hale telescope was the biggest telescope in the world before I was born. It was the biggest telescope in the world through my childhood. It was the biggest telescope in the world for half of my life. And as a scientific instrument, the fact that it's been at the cutting edge of astronomy for half a century is absolutely incredible. And it's testament to the astronomers who designed it, the engineers and technicians who built it, and above all, the person who had the vision to bring it all together, George Ellery Hale. Thank you very much for listening.